All right, let's get started. Before we start, Nick wants to say a little bit about SI. So, Nick. Guys, attention, please. Okay, go ahead, Nick. Nick, for those people who have never been to an SI session, can you briefly describe the kind of things that you do during an SI session? Any question for Nick? Cool. All right. So please do check out SI sessions if you like to get some extra help outside the other resources of help we have for you. All right. Today we're going to look at section 4.2. We're going to look at this thing called the mean value theorem. Okay, so before we talk about the mean value theorem, there's another theorem that kind of leads up to it that I'll describe first. There's a theorem called Rolle's theorem. This is named after a French mathematician, Michel Rolle, who lived during the second half of the 17th century. And he described this discovery here. If we have a function, let's call that f of x, and if these three conditions are met, we want the function to be continuous on some interval, closed interval from a to b. X is from a to b, including the endpoints. Continuous function. We want this function to be differentiable. On the open interval, so a slightly less demanding requirement here, differentiable anywhere from a to b, but possibly not at a or b. And 3, we want this function to have the same end y value. We want f at a to be equal to f at b. If all 3 of these conditions are met, the function is continuous, no holes, no asymptotes, no jumps of any sort. Differentiable meaning it's smooth, no cusps, no corners, and the same y values at the endpoints. Then there is at least one c, we'll call this number c, that's somewhere between a and b, where f prime of c is equal to 0. Okay, so that's Rolle's theorem. Let's go back and look at each one of these a little bit. I said earlier, for something to be continuous, remember, this means that there are no gaps, no jumps of any sort, no open circles, and obviously no asymptotes. For something to be differentiable, we want this to be smooth. No corners, no cusp. And this just means that we have the same y at the ends. Okay, now I want you to sketch at least one graph that meets, any graph you want, that meets all three of these conditions. And I want you to check if there is at least one place between A and B, whatever you made them to be, where the tangent line is horizontal. So sketch any graph that meets all three of these conditions and see if that's true. Any graph that's continuous, any graph that's smooth, any graph that has the same y values at the endpoints, whatever A and B are. Okay, were you able to find at least one location where the tangent line is horizontal? Yeah? Right, you should be able to find at least one. Let me show you a few possible graphs. We'll make A and B whatever we want them to be. Just leave them as A and B. Give them the same y value. So whatever graph you want this to be, it has to be continuous and smooth. So how about that? Okay, so continuous, obviously continuous, smooth, no corners, no cusp, the same y values at the two end points. And notice that I could actually find three places. One here, and one here, where the tangent line is horizontal. Let's sketch another one. Here's A and here's B. As long as you have the same starting and end y values, you can sketch whatever you want. Something like that, right? It doesn't matter how crazy it gets. And if you just eyeball across this thing here, we have one place with a horizontal tangent line here, one here. Looks like there's one here, maybe. One here, one here, one here. There should be at least one, possibly multiple of them. Okay, this seems like a very obvious result, right? If you know something is continuous, differentiable, and the same y values, then somewhere along the line, along the interval, you can find horizontal tangent line locations. Seemed obvious, but back when people were starting to develop calculus, this was not something that, well, it seemed obvious, but actually being able to state it clearly and concisely and without any kind of error was actually a challenge for the mathematicians back then. Let's look at a couple of functions where we have the function without a graph and see if Rolle's theorem is true. Let's have 3 minus 20x plus 2x squared. And we'll look at the interval from 4 to 6. Okay, suppose the question is, can you say, without doing anything excessive, that there is at least one place between 4 and 6 where the tangent line would be horizontal? And we know that's going to happen at least one place if Rolle's theorem's requirements are met. So let's check the requirements. First one, is this thing continuous on 4 to 6, including the endpoints? So what do you think? Yes? No? Yes? Why? How do we know? It's a polynomial, absolutely, yeah. Okay, so that is where knowing that the behavior of certain functions is really helpful. Is it differentiable on 4 to 6? Don't worry about the change in the end parentheses from brackets to parentheses. All it says is that is this thing differentiable on the entire interval? It's okay to be not differentiable at the endpoints for the second requirement. So is it differentiable? Why is that? Why do you think so? It's a parabola, which is a polynomial, which is defined for all. Right, so yes. Because f prime of x is also a polynomial. Which is defined everywhere. Okay, so if the derivative is defined everywhere, then clearly it's differentiable everywhere, right? So polynomial, differentiable everywhere, and also continuous everywhere. Last one is, are the endpoints the same? And this is just simple plugging in and checking. Plug 4 into here, we get 3 minus 80 plus 32. Yeah. It turns out to be minus 45. Plug 6 into there, we get 3 minus 120 plus 2 times 36, 72. And it should turn out to be also 45. Because all three requirements are met, Rolle's theorem guarantees at least one place where the derivative is 0 between x is equal to 4 and x is equal to 6. Okay, so how is this useful? Suppose you're looking for the absolute maximum and minimum of this function on that interval. If you know, remember, we have to check where the tangent lines are horizontal, right? As one of the things we have to check. If you know beforehand there's no such location, then there's no reason to check. There's no reason to differentiate and set equal to 0 and solve that. You simply check the endpoints and you're done with it, right? So that's where it can be useful. For a polynomial, it's not that big a deal. We can differentiate that very easily. But for a more complicated function, maybe you don't want to do that. Okay, so let's check. Let's see. If we actually go ahead and do that, derivative is minus 20 plus 4x. Make that equal to 0, and we see that x is equal to 5. All right. So that's what we're told, that there's at least one place we found 1 at 5, somewhere between 4 and 6. Depending on the function, there could be multiple, could be more than 1, but we know there's at least 1. Questions? Okay. All right, so let's check out this next one. One minus x to the 2 over 3 on the interval minus 1 to 1. Like the last example, we'll check the requirements of Rolle's theorem. First, is this thing continuous? All three requirements have to be met. If any one of those is not met, then Rolle's theorem cannot be used to guarantee that at least one location with a flat tangent line. Okay, so is this thing continuous? That interval. What do you think? Yes, and how do you know? It's not a polynomial. No, it's not a polynomial. A polynomial can only have positive integer power. This is not a polynomial. This thing's got a fractional power, so it's not. So we can't use the fact that polynomials are defined for all values to say that. Can you find any value between minus 1 and 1, including those two, where f of x would fail to exist? Can you take the 2/3 power of a negative number? Right, you can take the cube root of a negative, so that's fine, and then you square that, so that's perfectly okay. Okay, so what's our conclusion then? Is it continuous? Hold on a second, let me close that door. While I do that, keep thinking. Okay, what do you think? Yes? No? Don't care? Oh, you cannot care. Okay, that's not good enough. The answer is yes. Okay, for example, at x is equal to minus 1, f of minus 1 is 1 minus 1 to the 2/3. think of minus 1 to the 2/3 as the cube root of minus 1, which is a perfectly legal operation. You can take the cube root of a negative number, and then you square that. So this gives you 1 minus, that's a minus 1, squared, that's a 1, of course, and that's 0, right? So any number between those two ends, you will get a meaningful number out of it, and that makes it continuous. Continuous means that every x will give you a meaningful value of y, and that is the case for all of that. How about its differentiability? It's not. What's wrong with it? Right. Absolutely right. Yep. Perfect. So here's what he said. No. Because look at the derivative. It's that x to the minus 1/3 that's causing problem. Because this is equivalent to negative 2 over 3 times the cube root of x downstairs. Okay. Power of negative 1/3 means going downstairs and giving a power of 1/3, which is cube root. Clearly, there's a problem at 0. Okay, so that is clearly not differentiable on the entire interval, right? It's differentiable everywhere else, but not at that place. So you cannot say it is differentiable on the entire interval. So the second requirement is not met. The third requirement really is irrelevant, but we'll check it anyway. At minus 1, it's 0, of course. At 1, it's also 0. Okay. So, but it's irrelevant. And what this means is that Rolle's theorem cannot be used to guarantee the existence of horizontal tangent line between minus 1 and 1. And all this is saying is that there may still be such a location. There may not be. We don't know. But Rolle's theorem cannot be used as a shortcut to make that conclusion anymore. So if you were looking for the absolute max and min, then you would go through your regular procedure. Find where the derivative is 0 or undefined, and then check the endpoints together with those places. If you could use Rolle's theorem to rule out the possibility of any number between the two endpoints, then you simply check the two endpoints. Okay, questions? All right, so now we're going to talk about the mean value theorem, which is an extension of Rolle's theorem. It actually took them a century to make that extension. But let's take a look at what this theorem says. The only thing different between the two is that we're going to remove the third requirement. we still require the function to be continuous and differentiable from a to b, the same first and second requirements. But the third one will remove that. We no longer require that. And what the mean value theorem says is that, I'll sketch the graph and you can see. It's another theorem that it's very obvious once you've seen the graph. So let's make f of a down here, f of b up here. They don't have to be the same anymore. And I'll sketch a continuous graph and differentiable graph, so polynomial. Still continuous, still differentiable, okay, now look at the slope of the secant line between the two endpoints. Slope of that dotted line here is f of b, y2 minus y1, f of a over x2 minus x1, b minus a. Notice that there's at least one place on the graph where the tangent line slope is equal to the secant line slope. And on this graph here, we can kind of eyeball that. It's probably going to be right here. Okay, so that's the minor tweak between Rolle's theorem and what's called the mean value theorem. It's called the mean value theorem here because we're looking for the average slope. And mean is another word for average. The average of the slope, the mean value of the slope between the 2 points. Somewhere on the graph, we're going to see that. So that's called the mean value theorem. If the function is 1, continuous, on a to b, differentiable on a to b, just like Rolle's theorem. And those are the only two requirements. Then, there's at least one C, where C is between A and B. Where f prime of C, the local tangent line, has the same slope as the secant line between the two endpoints. Okay, so it's a generalization of Rolle's theorem. Rolle's theorem says that we can find a flat tangent line, flat secant line, flat tangent line somewhere between the two ends if the secant line slope is flat. All this does is that saying, instead of just talking about a flat secant line, let's talk about secant line of any slope. And that's still going to be the case as long as the conditions are met, continuous and differentiable. So this took them a little bit while to come up with this theorem about a century after Rolle did his stuff. And this theorem is due to another mathematician named Lagrange. Lagrange was French. Okay? French guy. Worked for Napoleon at some point. Respected by Napoleon and all that. Okay? So that's the mean value theorem. Let me give you a couple examples. The function is sine of x on the interval 0 to 2 inclusive. Go through the two requirements. They're exactly the same as Rolle's theorem's requirements. Is that thing continuous? Is sine of x continuous from 0 to pi over 2? Yeah, that should be pretty obvious, right? We know what sine looks like. It's just going up and down. It's always defined. Cosine is also defined for all x. What about tangent? If this were tangent here, would the question be yes or no? Pi over 2, 3 pi over 2, 5 pi over 2, and so on. So yeah, if this were tangent, then the answer would be no. But sine is defined for everything. 2, differentiable. Well, yes, yeah, you're right. Because f prime is cosine which is also defined for all values of x. So obviously including 0 and pi over 2. Okay, so this means that the mean value theorem guarantees at least one place between 0 and pi over 2 where the tangent line slope will be equal to the secant line slope. Where f prime of x is equal to the secant line slope. So sine at pi over 2 minus sine at 0 over pi over 2 minus 0. That's the secant line slope connecting the two to n. Let me sketch that. We know sine starts at 0 and goes to 1 at pi over 2. And between the two, it goes something like that. And here's the secant line. And that thing has a slope that's equal to that, right? y2 minus y1 over x2 minus x1. Okay, so it guarantees at least one place. Let's find out what it is. Secant line slope along the tangent curve, a sine curve is cosine. And now we want cosine to be equal to this. And that turns out to be 1 over pi over 2 or 2 over pi. And the solution to that is cosine, the inverse cosine of 2 over pi. Even without knowing that value, I know this is a first quadrant value. This is a positive number. Cosine positive must be in the fourth or the first. The context tells us this must be a first quadrant value. So even without knowing what it exactly is, we're guaranteed that it's in the right location. First quadrant value. And if you have a calculator, you can find it turns out to be 0.88 or so. Pi over 2 is 1.7, 1.5, 1.57, 1.58 kind of thing. So that's about halfway between the two, roughly, a little bit less than halfway. Okay, again, this seems obvious, but once you've seen a picture, it is obvious. All it is saying is that we can use the information about the properties of the graph and then use the shape information to make that determination. Any question on this? Okay. Yeah, I know this is not terribly exciting, but this is the beginning of the part where we investigate the shapes of functions. Let's do one more example and then we'll end it there. If we know f of 1 is equal to 2, and we know the slope of the tangent line is at least 3, greater than or equal to 3, for x between 1 and 5. We want to find out the smallest possible value of f of 5. Okay, we know one location where we start. We know the slope of the tangent line on this interval. We know that for certain. It's no smaller than 3 on 1 to 5. We're looking for the smallest possible value of 5. I'll show you two ways to handle this thing here. First, we'll use mean value theorem. And then we'll look at the graph of that, and it'll seem awfully obvious to you. So starting with the mean value theorem, we'll see how that works. If we know for sure the value of the tangent line, the derivative is always at least 3. If we know that on this interval, then we know that f of x is differentiable. On 1 to 5. Otherwise, we can't say it's at least 3. Differentiable means that the derivative always has a meaningful value. And we do have that going on here. Okay? If you're telling you the slope of tangent line is always at least 3, then that's saying that it is differentiable on that. If the function is differentiable, it is automatically continuous. Continuity is a requirement for differentiability. So if you know something is differentiable, like we got going on here, it is automatically continuous. And therefore, what we know just from this simple statement here, by interpreting what's given to us, the function f of x meets both requirements of the mean value theorem. On the interval 1 to 5. Right? We're guaranteed, because it is differentiable, we're told in a different way that it is differentiable, then it is automatically continuous. If it's continuous and differentiable, both requirements are met. And the mean value theorem therefore guarantees that somewhere on the function, somewhere on that function, we can find a place where the tangent line slope is equal to the secant line slope. This is what the mean value theorem tells us. And furthermore, we know whatever this turns out to be, it is automatically at least 3. Because we're told that f prime of x is greater than or equal to 3 on the interval 1 to 5. Okay, now focus on the right side of this thing here. We can say that f of 5 minus f of 1 must be greater than or equal to 3 times 4, right? There's a 4 downstairs. If I multiply both sides by 4, then we know that f of 5 minus f of 1 is greater than or equal to 3 times 4. So that means f of 5 is greater than or equal to 12 plus f of 1. I know what f of 1 is. It's given to me. 2. So this tells me that the f of 5 value has to be at least 14. Any question on this one? Okay, so that's mean value theorem. Now let's look at this from a graphical point of view. Okay, so what we did there was purely just using mathematics and knowledge of a function and just definitions of stuff. So we know we start with f of 1 is equal to 2. That's given to us. That's where we start. And here is 5. So therefore, what we're saying here is where in this strip is f of 5. It could live anywhere in that strip. It could be all the way up here, all the way down here. We don't know. But what we know from the statement is that the slope of the tangent line between here and here is at least 3. So if 3 is the minimum, the smallest it can ever take, no smaller than 3, then if you follow that along here, this must be the smallest value that f of 5 can be. So that's the minimum f of 5. We cannot follow a shallower slope because we're told that it is at least 3. It could be bigger than 3. If it's any bigger than 3, we'll get higher up here. But we cannot get any lower than. That's the minimum slope we can get. So if you do a little triangle here, this is 4. If the slope is equal to 3, then slope is rise over run, right? So this must be 12. That's the only way you can get a slope of 3. Okay, if you know this is 12, this is 2, then this guy must be 14. So that's geographically, that's how we can reason the same thing. We're using exactly the same concept that the mean value theorem is saying. Conversely, you can say that this is what mean value theorem is saying in words, but these two go hand in hand. They're the same thing, two sides of the same coin. Okay, so from here we can still see it's equal to 14. All right, so that's it. And like I said, we're starting to focus on the shape of graphs from this point on. We'll look at the graphs of things a little bit more on Friday and Monday. That's it. See you Friday.